Well, in the last video of this playlist, I have shown this. Data set. It contains the water density determined by students. Students analyzed this data set using descriptive statistics and doing box plots. They observed that the water density obtained is accurate because the mean values are close from the expected value. For example, the water density at run temperatures is close to 1, and the students get results that's very close for 1. They did box plots. We can also check data normality using box plots. For example, if a data set was normally distributed, in here we have the mean. The mean will put the box on the middle. And the size of the box also represents the precision. For example, if you have precise results, you have a small box, or simply a small interquartile range, or a small standard deviation. We can see here that I'm going to do this to make the picture more easy to be visualized. We can just do this, and JASP this software, we're going to organize the picture and make it easy to observe. Well, here we have results with the backer. The results with the backer. Now the software have organized the picture. You can do this to make your picture be easy to be visualized. We can see that results with the backer are less precise than results obtained with a graduated cylinder, a graduated pipette, and a volumetric pipette. And we also observed that this observation that has the number 31 was classified as outlier. We deleted these outlier results because outliers might strongly affect your data interpretation. So in spreadsheet number 2, all spreadsheets that I discussed in this playlist was provided as a Google Drive link. If we go to spreadsheet number 2, spreadsheet number 2 was showing here. It's the same as spreadsheet 1, but this outlier result was deleted. Now we are going to compare your results. We might compare the results obtained with the 4 glasswares using box plots. We can go to descriptive statistics, select the quantitative variable, and split according to the qualitative variable, which was the glassware which was used. It was split in here. We might also do box plots again. I like this ggplot color palette. This palette provided box plots with a good color, easy to interpretation. Now JASP was doing the statistical tests, but in this point I have something very important to bring to you in this video. As a professor, I can observe that when we have more than 2 means, that more than 2 average values that students want to compare, they simply goes and do one-way ANOVA. So students come in here, do one-way ANOVA, but they bring to here. They select the quantitative variable and they select the qualitative variable in here. And they obtain the one-way ANOVA interpretation of their data sets. Well, the box plot was already built. Looking to the box plots, you can see that the average values were relatively close. In this way, one-way ANOVA are going to compare the averages. But one-way ANOVA is a parametric test. What is a parametric test? Parametric test needs normally distributed data sets, and they need equivalent variances. Just looking for the box plot, I can see that the variances were not equivalent. So I cannot do a parametric test such as ANOVA ANOVA. I cannot do, because obviously the data obtained using a backer has a standard deviation different from the data obtained using the other two glassware. So if I simply go and use parametric tests such as ANOVA ANOVA, it provides a p-value of 0.7. So I conclude that the four glassware provide equivalent results, but this is not true, because I cannot use a parametric test in this situation where the backer provides a standard variation much higher than the other glassware. So when I go to one-way ANOVA, I must go to assumption checks. I have to check the variances. The Levene's test. The Levene's test check if the variances are equivalent. When I do the Levene's test, I can see that obviously the variances are not equivalent. So I cannot do a parametric test in this situation. I can use the Welch correction. I can do the Welch correction and try to use a parametric test in this situation. When I use the Welch correction, it provides a p-value lower than 0.001. And it showed to me that the data set was not normally distributed. It shows to me that the variances were not equivalent. And considering that variances are not equivalent, my four average values are not equivalent. Another option that I can do when I see that variances were not equivalent is to use a non-parametric test. I can use, for example, the Kruskal-Wallis test. So I am going to compare four different averages, which was the water density determined with four different glasswares, and now I am using a non-parametric test. This non-parametric test had shown to me that this data set, that these four results were not equivalent. So a student can conclude that using one-way ANOVA, that the four results are equivalent. When they do this, but they look for variances and see that the variances obtained using the backer are much higher than the variances obtained with the other three glasswares, and they use the Welch correction or the non-parametric test, the Kruskal-Wallis test, they can see that the results were not equivalent. The four averages are not equivalent. So where the difference lies? I can, the one-way ANOVA, the Kruskal-Wallis test, they just say to me that the averages are not equivalent, but they don't say where the difference lies. I can check where this difference lies using a post-hoc test. For example, one of the most used post-hoc tests is the 2K test. So I can see the 2K test and what this shows to me. Using the 2K test, the 2K test says to me that the four average values were equivalent. Oh, professor, but I believe that the results go against what you showed using one way or another. Yes, I have these results that were not realistic because the Tokay test is also a parametric test. I can use, for example, a test that was not parametric. For example, I can use that I have two other options, that is the DoNet and the DUN tests. This test might be more effective if I am analyzing a data set which was not normally distributed. The DUN test compared the other three glassware with the results obtained with the backer. It also shows that all results are equivalent, the DoNet test and the DUNS test have shown that we have some differences between the graduate cylinder and the graduate pipette. Well, in this situation, the post hoc tests were not useful because the data obtained with the backer has a standard deviations different from the other standard deviations. The standard deviations obtained for water densities using the other three glasswares. So, what's the main idea of this video? Is to show that when we are going to compare four different MEMS, you use ANOVA ANOVA, but ANOVA ANOVA is a parametric test. It needs normally distributed data set, and it needs equivalence of the variances. So you can check equivalent of the variances uses the Levine test. Once that Levine test show that your variances were not equivalent, you might use the Welch correction, or you can use the nonparametric tests, the Kruskal-Wallis test. Well, this is the idea of this video. Until the next one of this playlist.